So the types of operators that show up in Sturm-Liouville problems are called Sturm-Liouville operators, which we'll abbreviate by SLO. Yeah, I know. So a Sturm-Liouville operator takes y to the derivative of py prime plus qy. And again, p is continuously differentiable and q is just continuous. So we have an important idea of a self-adjoint operator, which is the generalized version of symmetric, if you think about symmetric matrices. So an operator L acting on an inner product space V is called self-adjoint if and only if you can move it from one side of an inner product to the other side, regardless of what vectors you've got in there. So let's consider the subspace of L2 of an interval that is comprised of functions satisfying these boundary conditions. Then any Sturm-Liouville operator acting on this subspace is going to be self-adjoint. So let's take a look at the proof for why this is true. Okay, well, we'll look at the difference between ULV and LUV. So let's see. So this is the integral from a to b ux lvx dx minus the integral from a to b v lu dx. And so if I now put in the operator there, then this is going to be, let's see, so we've got u times pv prime quantity prime plus u q v. That's the first one. And then the second one is going to be v pu prime prime plus v q u. And so let's see what we can do now. We'll do an integration by parts. And so that's going to pull out a boundary term of UPV. So what I'm doing is I'm using integration by parts here to move this prime onto the other factor. So I have to pay with a boundary term and then also a minus sign for the integral. So I'll have a to b and then u prime pv prime. But then I'm going to do the same thing for the other integral. And so for the other integral, that's going to give me a term that looks like, oh, sorry, there should be a prime here, minus vp u prime. And so then I have the other integral, which is going to be v prime p u prime. And I forgot to point this out, but this term cancels with this term because of the minus sign right here. So we don't have to worry about those. Those are gone. And speaking of cancellation, now we see that the integrand here actually zeroes out. And so all we're left with is this part. And I can factor the p out of there. And then you notice that we're looking at uv prime minus vu prime. And that's exactly the determinant of the matrix that has uv, u prime, v prime. And that determinant is called the Wronskian. And so typically we denote the Wronskian of u and v with this w here. I'll just call it w for short. And that's exactly this, where you put the functions across the top and then their derivatives across the next row, like that. And so what we have here is px times the Wronskian at x evaluated from a to b. And it turns out that this is 0 at B and 0 at A. And so to see why that's true, we look at the boundary conditions. So if you look at the boundary conditions, say at x equal A, what do we have? Well, what we're looking at then is UA, U prime at A, V at A, V prime at A, multiplied by alpha 1, alpha 2. And that's by the way our boundary conditions are set up. Those two linear combinations should be equal to 0. And now our requirement is that alpha 1 and alpha 2 not both be 0, which means that we are requiring a non-trivial solution to this homogeneous equation. And if you remember your linear algebra, that means that this matrix here has to be singular, non-invertible. And so that matrix is non-invertible or singular if and only if its determinant is equal to 0. So then that tells you that its determinant, which is equal to W, has to be 0 at A. If you recall, the determinant of the transpose is equal to the determinant of the original matrix. So even though this one that we looked at up here is the transpose of this one here, they both still have the same determinant. Okay, and so the exact same argument works at B. And so as a consequence, we see that our boundary term vanishes. And then that tells us that these two terms have to be equal because their difference is 0. And that gives us the proof. And this is the reason why we like Sturm-Liouville operators, because they are self-adjoint. That's why they're useful. If you examine the proof also, we can pick up a corollary, and this is called Lagrange's identity. And so just looking at the sort of the middle of the proof there, you can see that ULV minus VLU is the derivative of P times the Wronskian. And so sometimes that's useful. And I just realized that I went through this whole thing assuming everything in the world is real valued, but of course it's not. So a couple of things I should have pointed out is that P and Q are both need to be real valued functions, or else the Sturm-Liouville operator will not be self-adjoint. And so also, let's see, when I put these guys into the inner product up here, I need to include the fact that there's a conjugate on this guy and a conjugate on this guy. Now the conjugate on the LU becomes conjugate L conjugate U, but then because P and Q are both real valued, it turns out that this conjugate doesn't matter. Now, if we continue on with the conjugate that is there, just put a bar on every single U all the way through here. The derivative of the conjugate is the conjugate of the derivative, blah, 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 all the way through. It doesn't matter to the very bitter end. Just stick a conjugate everywhere, and the whole thing still works. So, yeah, just wanted to make that correction.